In this section, we will introduce two additional notations associated with partial derivatives of functions of space, especially with three-dimensional space. The first one we will discuss is what is called the Laplacian. It's a generalization to a second spatial derivative of the ideas of curvatures in three-dimensional space. The second notation we're going to introduce is called the gradient, and it is a generalization of the first spatial derivative. These notations and concepts occur very often in describing the physical world. So, thus far we have thought about functions of one spatial direction, or of two spatial directions, such as the height of a hill. We also have to be able to think about functions that can depend on all three spatial directions, such as the pressure of a gas. In principle, that pressure could be different at every point in three-dimensional space. Another example like that would be the density of something in space, such as the density of a smoke cloud. As we will see here, the gradient and the Laplacian usefully become the corresponding first and second derivatives of such scalar quantities in three-dimensional space. We will mostly see how and why these are useful later once we consider various physical systems. So for the moment, we mostly introduce them just as notations. So let's look at the Laplacian operator. It can be defined for ordinary Cartesian coordinates as the sum of the three spatial second derivatives, partial d2 by dx squared plus partial d2 by dy squared plus partial d2 by dz squared. A convenient way to say the Laplacian operator is del squared. Sometimes it's written just with this character here instead of the del squared version I've written here, though I am not going to use that notation. So for example, if we propose a three-dimensional wave equation where we have a second spatial derivative for each of the three Cartesian directions, and still the same time derivatives over here, we can write this more compactly using the Laplacian notation as simply del squared phi minus 1 over c squared d2 phi by dt squared, all partial derivatives, of course. Even more compactly, we might not bother to write out all of these variables here, and you'll often see the three-dimensional wave equation written in this form here. And with some simplifying assumptions, this turns out to be a very useful equation in a lot of classical physics. It describes many acoustic waves and can also describe electromagnetic waves, again, under some simplifying assumptions. The gradient operator is defined for a scalar function f as the gradient of f is the unit vector in the x direction I times the partial derivative df by dx plus the unit vector in the y direction j times the partial derivative df by dy plus the unit vector in the z direction k times the partial derivative df by dz. If we were just working in two dimensions, we could also use the gradient, and it's a little easier to envisage it in two dimensions. So for some function h of only x and y, such as the height of a hill, we could define a two-dimensional gradient here, just involving the partial derivative with respect to x and the vector direction I, unit vector, and the partial derivative with respect to y and the unit vector j in the y direction. And here we might use some notation like putting a subscript xy underneath the gradient operator sign here to indicate we were only working with those two variables. The real usefulness of the gradient operator is that it gives both the magnitude and the vector direction of the largest slope. So if you were standing on the hill and you pointed yourself in the direction which was the direction of the steepest gradient on the hill, the magnitude of that gradient would be the magnitude of the gradient, grad f, and the vector direction of that gradient that you were pointing in would be the vector direction of the gradient of f. Note that although grad f here has no bold font or other vector notation, it is a vector quantity. So this gradient operation turns a scalar into a vector. And as I said earlier, we do sometimes allow ourselves to put subscripts on this operator for clarity on how many and what coordinates we are considering, as we showed earlier on with the gradient of our hill. And this symbol here can be called del, or sometimes nabla, though I won't use that notation. So we could say this is del of f, but we would usually say grad f, or gradient of f.